Hi guys, welcome. Today we're going to be looking at success in a large sample. Okay, so we've started looking into the real distribution part of this option, where we've been looking at the central limit theorem. Hopefully you've got a basic idea of what that is and how it works at this point. We're going to move into looking at large samples, right? Because part of the point of all this is we want to be able to consider if my sample, if my population is really, really large, how do I deal with finding statistics about that population? And how do I know if statistics that are presented are true, and how can I test those things, right? So keep in mind that as we go through this is all based off of probabilities, right? And so there's nothing that's going to be 100% certain. It's always got to be some type of probability, which means there's always a chance that we're going to be wrong. All right, but we can be fairly confident much of the time. Okay, and we'll look at that today, at least part of that. Okay, so I want you to consider just a minute. You know, when you read statistics in the news, you read about so many percent of people voted for this candidate, or such and such percentage of people are smokers, or such and such percent. Now the coronavirus is big, so such and such percent of people are in a specific city are getting the virus, or such and such percent are recovering, or those types of things. Now, in some of those cases, like the coronavirus, that's as close to accurate as we can be, because they're actually taking data from every single person that they know of that is getting that. Okay, so that's a different situation. But when we talk about the percentage of people that are smokers, or the percentage of people that voted for a candidate in polls and in primaries and things like that, it's a different scenario, because we don't actually ask every single person when they leave the poll, and there's a possibility that when they leave the poll that they lied about who they voted for, and same thing with smoking and things like that. So what we're looking at here is we're looking at taking a very large sample, as large as we can get, but still not being able to look at the whole population. All right, so that's kind of what we're looking at today. When we talk about this, we're going to be talking about what we call the sample proportion. Okay, so sample proportion, which is usually shown with a P with a hat on top. Okay, and the sample proportion is just represented by X over N, where X is the total number of successes in our poll or in our event, right? So it could be the number of people voting for the Democratic candidate, or the number of people, again, that are smokers or whatever. So that's the total number of successes divided by the number of people in our sample. And that gives us what we call the sample proportion. And it's a sample proportion because it's a proportion of the successes that we get, or the probability of success, but it's not the probability of the whole population, it's just of that sample. All right, so that's the idea that we're going to be looking at today. So for example, if we're looking at a particular candidate, and we take a poll as people come out of the polling booth, and we ask, let's say that we ask 3,500 voters who they voted for, and 1,820 voted for our candidate, okay, candidate A. All right, now the sample proportion is pretty straightforward, because that just means that we take the total number of successes, which is 1820, and we divide by the total number of events, which is 3,500 voters. Okay, so that part of it is fairly straightforward, fairly easy to work with. All right, but now we're going to look into some things with variance, expected value, and things like that that are going to make it that are going to allow us to do a little bit more with the statistics, but it is going to be a little bit more difficult to deal with. All right, so let's go ahead and move on to that. Okay, so still looking at success in a large sample. So before, we defined X as being the total number of successes. Okay? Now, because x is the total number of successes, we're going to define y as an individual event. Okay? An individual event. Okay? In the case of the people coming out of the poll booth, each y is a particular person, right? So y1 would be the first person that we asked. y2 would be the second person we asked. y3 would be the third person we asked, right? So given that there's a certain proportion or probability of people that actually voted for candidate A, so we're gonna let's look at that actually were a success. Okay, right here we're gonna be saying that y equals 1 if it's true or success, and then y will be 0 if it's false or if it's a fail. All right, so the first thing I want us to do is let's look at the expected value of p. Okay, so the expected value of the p hat, sorry. Okay, now remember that means that we have individual events happening, right? So we have event 1, event 2, event 3. So this is the expected value of getting y1 plus y2 plus y3 all the way up to however many there are, yn, all divided by how many trials there are. Okay. Now this, of course, the n is a constant, so I can pull that out. So I'm going to have 1 over n times e times y1 plus y2 plus y3 all the way up to yn. Okay. Now at this point, we know that the expected all of these y's added together are going to give me x, right? The total number of successes. And we know that the expected value, this is a binomial probability, right? Each one of these is a Bernoulli. Either it's a 1 true or a 0 false. When I add all those together, I should get x. When I do each one of them, if p is the probability of success, now this is the actual probability from the whole population, right? Before, we were talking about the sample proportion, which is the probability of our sample, right? Now, for the population, okay, it's actually the normal p. So if I take one guy, the probability that he is going to have success is p. And so really what I get here is 1 over n, e times probability of success here, the expected value of y is just p, right? But then I've got plus p, plus p, plus p. So when I add all of those together, then the sum will be np, because that's the expected value. And so it'll be 1 over n times np, because that's the expected value of all of those. And the result then is p. Now, this should kind of make sense. And the question is, well, why did we go through all that to show that the sample proportion is, or the expected value of the sample proportion is the same as the proportion of the population? Well, we want to make sure that the mathematics actually works out. And so what I do want you to see here is exactly that the expected value of the sample proportion, what do we expect to get when we take this sample? Well, we expect to get the same thing, that is the probability of success for the population. That's what we expect to get. Okay, now realistically, we learned last time that that doesn't happen, right? We got the central limit theorem, which says on average, they are going to be towards the middle. We are going to get close to this p, but sometimes it's going to be a little bit more, sometimes it's going to be a little bit less. But with a large population, it's going to be a normal distribution, and we're going to be pretty close to this p most of the time. All right? Okay, let's move that up. We're now going to look at, of course, variance. Okay, so now we're going to do the same thing with variance. All right, so we're going to say we want the variance of y1 plus y2. Sorry, I changed my y there. Plus y3 all the way up to yn all over n. Okay, and we know that with variance, when we pull out that 1 over n, it becomes 1 over n squared, because we have to square the thing that we pull out of, sorry, that shouldn't be a parentheses yet, times the, I did it again. It's all right. You get it. y1 plus y2 plus y3 all the way up to yn. All right. Now, we know that this, once we've got the sums, that of course we can rewrite it as the variance of y1. This is using that expectation algebra that you learned back at the beginning of this option, all the way up to the variance of yn. And you know what the variance is for a Bernoulli, right? For a Bernoulli, you can look it up, you can go remind yourself what it is, but the variance for a Bernoulli is p times 1 minus p, okay? And then I have, of course, n of those. And so this now gives us 1 over n squared times n, because I have n of these, and then the variance, of course, was p times 1 minus p. Okay, there you go. And when we put all that together, we get the variance of our sample population, which was this, right? Variance of the sample population should be, cancel out one of those n's, p times 1 minus p over n. All right, so we now know how to get the expected value of the sample population. We also know how to get the variance of the sample population, okay? And so this is going to help us when we try to answer questions about this. Basically, what it means is that for a sample population, it has a distribution, right? It has an expected value, it has a variance, and because we're taking a large sample, it means that it must have some type of normal distribution. And so the normal distribution of the sample population depends on its expected value, which was p, and its variance, which was p times 1 minus p over n. And that's the distribution that we're going to be working with. All right. Now, remember that we still have our x initially. Remember, x was defined as the total number of successes, right? And so that means that ex, the expected value of x, is the expected value of n times p, right? Because that's our sample population, and we multiply by the number of times that occurs. We should be able to pull the n out, and so we get n expected value of p, which is, as we expect, np, as we just learned, the expected value. So the expected value of x equals np, as expected. And then we got the variance of x, right, which is getting a specific number of successes. So that's equal to the variance, again, of n times sample population. Pull out the n. That gives us n squared. Variance of p. We just found out that the variance of p was this right here. So now we have n squared times p times 1 minus p over n. And we find out that the variance of the total is n times p times 1 minus p. There we go. So everything works out the way that we expect it to. Okay, we got everything fine. So we're going to go ahead and move on to an example now. All right, so that you have an example of how this might work. I don't know if you guys have ever read the books, series of Unfortunate Events, or maybe read or watched the videos on Netflix. If you haven't, it's kind of a fun watch, fun read. Got some different types of humor in there, satire maybe, I don't know. But anyway, give it a good watch. It's a fun thing to watch. Maybe now that you've got some extra time, or you need something to something to spend some time on now that you're at home all the time. Watch it on Netflix. There's in this book, the Baudelaire orphans is who the book is about, and they're constantly fighting against this guy named Count Olaf. And he has a newspaper that he and his henchmen produce called the Daily Punctilio. And so I thought this was an interesting version of the question that the textbook asked, so that we could add that in for those of you who have read it or whatever. So here's the question. The Daily Punctilio reports that Count Olaf got 62% of votes in local council elections. Assuming this is true, if the sample size is 150, so they asked 150 people, what is the probability that a poll would show Olaf with more than 50% of votes? Now, a caveat before I start this, I do not have a calculator with me. Given that that's the case, I'm going to be able to go through and do the setup with you, but I need for you to actually go through and do the calculations and hopefully be able to get some answers there. All right. So here we go. Assuming this is true, if the sample size is 150, what's the probability that the poll would show Olaf with more than 50% of votes? All right. So we are looking at that our sample population has a distribution of a normal distribution. Okay. It says that he got 62% of votes. So if we're assuming that that's true, that means that the actual probability of somebody voting for him is 0.62. So we're going to put 0.62 here. And then the variance from the previous slide, the variance, remember, was p times 1 minus p over n. So that'll be 0.62 times 1 minus 0.62 all over n. N was 150, just like that. And so you've got your normal distribution. So the question then is, what is the probability that he's going to be more than 50% of votes? All right. So you should be able to go straight into your calculator. You should be able to calculate the probability that P is greater than 0.5 for that 50%, and just use a normal distribution calculation in order to be able to do that. All right, you should get a pretty high percentage, right? Because the reality is that 62% of people are voting for him. So what's the probability that my poll is going to say more than 50%? Well, it's pretty good. All right, so you should get a number pretty close to 1. All right. The second question asks, well, what if the sample size is 750? Well, that's not going to change much. It just means that my sample proportion then is the probability is still the same. Okay, 0.62 times 1 minus 0.62. But this time, instead of 150 on the bottom, I'm going to have 750 on the bottom. Now, of course, what that does is, because I have more data points, it means that I'm going to have a smaller variance, a smaller standard deviation. So whereas before my sample populations would be something like this, where I have an expected value, but I could be getting other values, now it's going to be much, much skinnier and narrower and taller right there. And so I'm going to be more certain in my outcomes. So this time, when you do this, you should get a number that is even closer to 1 than the previous one, right? Because I'm taking more data, and so I should be closer to the real value, the expected value, okay? And so therefore, both of these should show that there's a pretty good probability that I'm going to be showing that Olaf's going to win, that he's going to have more than 50% of the votes. All right? Now, this is the one that I really want you to be able to focus on and think about. Okay, those applied the ideas to a simple mathematics situation, but I want you now to be able to get a result and think about it. So the Baudelaire orphans now go out and snuck around and asked 100 people who they voted for. And they found out that 43% of those polled, voted for Olaf. Okay, so they're finding something. This is actually what really happened, they went out and they got 43% that voted for Olaf. Okay, so we're going to find out what is the probability of that happening. Okay, now, so the way that we're going to do that is we're going to say, okay, we now have a new sample population. Okay, we're not assuming this is correct anymore. Okay, this population, our expected value, we measured 43%, so 0.43, which means I'm going to have 0.43 times 1 minus 0.43 all over the total, which was 100. Okay, now what I want to know is what is the probability that my sample population is greater than or equal to the original value, 0.62. Okay, because I want to know what is the probability that this actually happened if the original was true. All right, so what is the probability that I'm going to get this expected value and I'm going to get this variance, okay, given that this is actually true? All right, so what do you get? Well, you should get a probability that is really, really, really low. Okay, so the fact that you got a probability that's really, really, really low means that if this is true, if they went out and got this real data, the probability that this is actually true is very, very low, which means that the original statistic is probably fabricated, that it's probably not true, because the probability of it occurring with the data that we actually gathered is very, very slim, right? So that's basically what we wanted to do, was to be able to say, okay, we have some information given to us. Let's go take our own data and then we'll compare it and see if the original is likely or not. Okay, so hopefully that makes sense. If you have any questions about that, just shoot me an email, or a note in Teams, and I'll try to help you out. This assignment's going to be a little bit shorter today. You're just going to be practicing this idea a couple of times, and then next class we'll move on with something a little bit different. All right, thanks. Good luck.